Welcome back. And now we're doing the final session of the workshop where we're going to talk about where do we go from here, future directions. So if you recall, one of the objectives of this workshop is to bring the community together and share what has already been accomplished and what each of us are working on. And speaking from experience at JPL here, it's one thing to work alone or try to develop interesting ideas. It's a completely different thing to put it into a polished format or a product that you can give to actual project submissions and to rely on. They usually do not have a lot of tolerance for things that do not work. So focus on providing solutions that work, tools that work is very important. So the Open Caesar project has tried to provide this level of maturity to its user base in order to encourage adoption. So in this talk, I want to, you can think of this talk as a kickoff to the next session on the panel, where we will talk about how do we collaborate, what do we work on as a community. So it will just throw in some future directions. I put this presentation from the lens of what the work we've done in Open Caesar, but of course I realize this is not all the R&D directions that are out there. But now that we have shared what we are working on, we can together as a community put an agenda for the group to try to aim for, and maybe we come next year and we present what we did on that vision. So I wanted to just introduce this idea that you may have seen in the questionnaire that we put to, that you had an opportunity to fill, which is the need for an ecosystem for this area of ontological modeling analysis in the context of MBSE. So I'll speak a bit about that need, and then we talk about some of the ideas for future directions. In this case, I'll motivate them by the needs that exist, the gaps that, from my perspective at least. So the idea of an open source software ecosystem is not a new thing that it has been around for some time. And in fact, I want to use an example of an already established like ecosystem on Eclipse. It's called the Eclipse modeling framework. This framework has been there for now like over 20 years. It's very mature, and it has attracted a lot of members, a lot of technology and engineering teams building on top of each other's work. Usually such an ecosystem has some core foundation. At its core, there is some foundational technology, and then everything else is built on top of that. In this case, the foundational technology was it's called the Eclipse modeling language, and it's an implementation of the OMG's MOF, or I should say essential MOF specification. So this foundational technology is meant to be able to represent information according to that specification. But then to make it usable, to make people want to use it, you need much more than just a way to represent information. You need a way to author information. You need a way to federate information, to integrate information, to analyze information, to report information. And each one of these areas have a lot of needs. For example, take collaboration. What does it mean to provide an environment that we can collaborate on? You need, for example, a way to be able to say what were the differences in the ontologies or in the models. How can we present that? Do we present this for the peer review process from the author perspective or from the stakeholder perspective, and how to use that to drive the peer review process? And for example, how do you integrate tools together? You need transformation. So we need transformation languages. We need tools that support these things and so forth. So what I mean by ecosystem, it's a set of integrated suite of tools. There is a foundation at the core of this ecosystem that we kind of need to agree on, the building block, and then we can build these capabilities on top. And the thing is, if we are a community and each one of us has taken interest in some area of the ecosystem to try to build it, then we can leverage off each other's work and build on them. And that's what projects like OpenCaesar and ontoUML and other projects we heard about today are trying to do. So since we are community who's interested in ontology, I thought we need to define what is that ontology stack, the foundation that we are that we all use. And this is an attempt at me showing how does this semantic web stack look like. You need a way to represent information, that's RDF, the linked data language. You need a way to query and update information in RDF, that's Sparkle. You need a way to validate the information, that's Shackle. You need an ontology language to actually give semantics to the data, that's OWL2DL, description logic in this case. And then you need a way to check the consistency of information based on that semantic, which is the swirl spec, the inference rule language. So I would say that's kind of like the minimal foundational stack that we can discuss and we can agree on. That can be the core foundation of any ecosystem that is dealing with semantic ontologies. And then we build on top of that stack. So that stack by itself, which is a bunch of standards that are useful, is one thing, but to actually make it practical and usable, you need more than just these standards. You need formats to interchange information in. You need APIs so that we can build tools that manipulate this information. We need databases that repositories where we can configuration manage and version control information and make it accessible through queries and update scripts. We need reasoners in order to be able to make sense of the information and check their consistency. And we need IDEs, like environments where we can author the information and analyze and project the information. And fortunately, the semantic web stack, the one that I presented in the previous slide, has a lot out of the box already for you. For example, these technologies that are mentioned already exist and they're open source. What we did is we took that as our starting point. However, we realized that we need more for this kind of ecosystem to be usable for MBSE. We needed, I'll start with this blue boxes. We needed, as I said, to agree on how exactly are we going to use ontologies to represent these system engineering vocabularies. And then we need a way to author information. We need IDEs, we need authoring tools, authoring viewpoints, and those need to be easy to build. That should not be too much trouble to be able to author information to address your user base needs. And then we need a way to configuration manage the information, also in an easy and effective way. You need ways to integrate the information, federate the information, and integrate the information. So federate, how can you split them? How can you define your methodology to allow you to split information into different repositories, give it to different authorities to work on, and then how can you allow these information from that federated set to be integrated together in a systematic way? What does it mean to be integrated? It usually means to run analysis. What kind of analysis do we need? Then how can we make the information in the ontologies available to our stakeholders? All these concerns are concerns that have to be part of our ecosystem. In addition to that, we need useful libraries out of the box so people do not have to start from scratch. They can take libraries and start from them. We also need examples that showcase how can we do all of this. We need tutorials and examples that we can learn from and maybe treat it as benchmark to build on. So I will go through these areas in a bit and just saying what are the challenges, what do we have today, and what we need to do next. So in terms of ability to represent system engineering vocabulary, we have the our 2DL as a specification along with the SWIR language in order to be specific about the vocabulary, syntax, and semantics. But out of the box, there is no guidance on how the information should be organized using such ontologies. What are the patterns that you need to build up as a foundation to represent the information? And we need to also make sure that however we are choosing to capture the information, it needs to scale well in reasoning. In our experience, not everything will scale well. You need to be very careful how you formulate your expression such that you get performance, because without that, you lose the benefit of the semantics. So today, with the work we've done in OML, at least we try to give a methodology of how to use OWL effectively in this sense. We introduced some abstractions to make it easier and not very intimidating to work with OWL in the common system engineering. And we carefully created a subset of the language that will allow expressions to scale when you reason on them. So think about the reasoner now as the compiler. It needs to just compile and work. It should not take hours and whatnot to do that. So in the future, as we said, we picked a subset of expressivity, the subset that allowed us so far to help for space projects in a variety of domains. However, it may not be the only set we need. We might need to grow the set, but instead of just accepting the entirety of the expression power, we need to be careful in how to grow this set so that we maintain performance and we maintain explainability. What I mean by that is when there is a problem, I need the reasoner to tell me what's wrong. That explanation needs to be easy to understand for me as a user. If I used a lot of, for example, anonymous classes everywhere, it would be very hard to communicate what has gone wrong. So we need to be careful on how to express such that we get explainable results. In the area of authoring, when you give an MBSE tool out of the box to anyone, they will not know exactly what to do. It's very overwhelming. What they need is a methodology. So a methodology, it breaks down the steps that they need to think about in order to do the job. And to do that, you need some viewpoints that make it easier for them to follow the methodology. First, you have to think, let's say, about requirements. Then you have to break them down and identify the main components. And then you have to do this and that. So every step in this fashion needs a dedicated view, a task-specific view that makes it easy to do. And that kind of view needs to cater to the needs of the people who are using the tools. And you need, of course, to enable collaboration, since anything beyond a small project will have issues with collaboration. So you need to think hard, how can you enable easy collaboration on projects such that you can scale up the work to the enterprise level. What we aim for is everybody should be doing system engineering with models and ontologies. How can we do that? So we have tried to achieve some of this capability in the OpenCSAR project today, but of course we're not done. What we have is we have an IDE that allows us to configure a methodology for an organization that's supported by vocabulary, supported by viewpoints that are easy to author. In fact, we use some frameworks are like low-code frameworks that allow us to quickly put these viewpoints. We have different viewpoints out of the box, like a text editor, and we have ability to do diff merge on models. The framework we're using is customizable. We haven't customized it much yet, but there is capability for it to customizable to make it even better for the viewpoint. And we need to develop some interfaces to existing tools that if you decided not to start with a new ontological tool, but you have another engineering tool out there that you want to use, we need ways to develop adapters or interfaces. We need APIs, ontology APIs, to allow us to do that. So where we're going from here, We have an Eclipse-based environment today. Tomorrow, our user base has asked us to do a web-based environment that also helps the operational side of MBSE, because if you had to support this, you have to install things on everybody's machine. That can take time and resources. Web-based deployment is easier, and we think we can accomplish that. We have you saw a prototype of this in Vision that we can take forward. We also need to make these methodology declarations like even lower code than they are today. And in OML Vision, we try to do this with just simple files, that JSON YAML files. You configure them and you get these viewpoints. We also we're using Git for collaboration, to do collaboration. We need to enable different kinds of collaboration methods, not only through the Git workflows, but also collaborative, like authoring, where two users, think of the Google Doc experience. Two people come in the same model and they start editing together. We need to assist to raise the level by creating a co-pilot. Think of that, a co-pilot for the methodology that understands that can help a modeler to create model and help answer questions about the model. A co-pilot is an interesting future direction, and we need to think about what are the common tools that our collective community would like to see adapters for, and we start having a plan to implement such adapters. In the area of configuration management, the various tools you're probably using have their own CM solutions. They use proprietary formats, and very few of them, if any, have good model differencing capabilities or user interface. That is a big problem for collaboration. And we need a way to protect baseline, to be able to audit history, to be able to make releases. All these features are needed in order to scale up configuration management to the enterprise. We've done some approaches. In this case, for example, we use Git, which out of the box supports a lot of use cases for collaboration, ability to divide work into commits, to put them in branches, to call peer review through this pull request mechanism. We can do more than a text def. We have a model def capability, but we need to improve it a bit more. And we do releases of individual repositories, and we put a semantic version tag, and we publish them to a place where other repositories can declare dependency on them, and dependency resolution mechanism is automatic. In fact, it's very powerful because with semantic versions, you can use static ranges or dynamic ranges that enable a lot of use cases. So where do we go from here? We need to improve this model diffing capability. Ideally, we want to have it that works in a viewpoint fashion, so that you can not only see the differences in terms of how the model itself or the ontology is structured, but how the view you're using is presented. In terms of the diagram you're using, in terms of the form, in terms of the tree, you want to see the diffs at that level so that your stakeholders, your authors can do it. But not only that, you also need to do it in terms of reports, documents that your stakeholders who review your work can understand. We need to support things like support of time travel. How did this report evolve over time? And you can go back and forth, for example. In the area of model integration, you need to be able to federate models. We cannot accept anymore everybody working in the same model repository. We had a lot of experience in this in the Europa project, where we have a lot of people editing the model, and without any control there, someone could accidentally delete something, and others have start building on top of that, and only to realize late this happened, and trying to recover from that is very hard. Also, when everybody's working on the same repo, it's very hard to keep track of who said what, because it's not clear which statements were added, attributed to which authority. So federation is giving everyone a piece, a repository to express what they want from their perspective. That could be a particular domain, particular subsystem, and then have a strategy to federate, to combine the information express traceability links and then express semantics of these things. What do they mean, so that you can use reasoners to check that consistency. So we need, for example, to allow the use of digital thread tools between ontological databases, but we also need maybe an ontology native digital thread solution. In the area of model analysis, analysis can take many forms, but I identified here 3 of them: consistency checking, completeness, and correctness. And by consistency, that's the most fundamental one, because if you cannot have confidence that your models are consistent, you cannot then move on to do anything else. This is the equivalent of writing code without a compiler. If your code doesn't compile, you cannot run it, you cannot do anything with it. So consistency checking is fundamental thing, and thanks to use of reasoner, you can get this if you did your job properly in giving semantics to ontology. The reasoner can help you with that. It can help you that say that your model consistent according to your vocabulary, doesn't have logical contradictions. After this, you build completeness and correctness. And completeness here, you have to think about it. There is no universal notion of correctness, of completeness. It depends on the phase of the project. So you need to specify that with rules and attribute this to phases of the project, how complete you should be at various steps in your process. And that have to be clearly identified and tooled, and so that you can communicate this to the tool. So today we have the logical reasoner, the DL reasoner that can do that. We have other abilities like Shackle and Sparkle that allow us to author queries that can be used to analyze completeness, for example. We can, if we want to engage other analysis tools like simulation tools, sophisticated other tools, these tools, we need to correctly characterize their inputs and their outputs ontologically. So we need to say, if you want to use analysis tool A, this analysis tool follows that ontology as input. So you could incorporate that ontology in your methodology, or have a way to map to it so that you can leverage this tool. So you don't have to create to only develop interfaces to analysis within your methodology. You can make it generic and pluggable into any methodology. So where we go from here, we want to improve on these capabilities. While consistency checking today, you get an explanation. It's a bit hard to understand it if you are not like an ontologist. So we need a way to make explanations a bit easier to see. We need ways to use other tools like code generators, model finders, and Jan showed us today what he called simulating the ontology. This is kind of under the hood using technological model finding, which shows you correct or valid instances of your ontology, so that you can check, did I create it correctly? Did I overspecify it? Did I underspecify it? That's a very useful tool. We need interfaces to simulation tools, so we need to define operational semantics as well as logical semantics, and we need to get use of those AI bots to help us achieve these things, to help us become a co-pilot for our practice. In terms of the model reporting capability, this is also another area, a challenging area. When you author a model, do you show it to your stakeholder using the authoring viewpoints that you use, those diagrams, those tables, or do you engineer viewpoints that cater to their needs? For example, I'm a math engineer, I want to see the math roll-up. That's the kind of view I want to see in order to judge if the change is acceptable or not. I don't care how exactly everything else is laid out. So by carefully working with our stakeholders, engineering to them viewpoints that cater to their needs, make those viewpoints easy to generate. From every commit even, every time you do a change or propose a change, a script should come up and generate that report for you. This is what you use for peer review and not maybe the original like authoring viewpoint. So today we have the ability to create some report templates, these viewpoints, and specify them rigorously with queries like with Sparkle. We have ways to mechanize the production of these reports with CI scripts, and we need also ways to publish them. We already kind of have ways where we publish these reports to a known place, a place that all stakeholders will go to see where is the baseline, and then if you have a proposal for change, they can find it and they can easily compare it. In the future, maybe we can generate these reports by prompts. I can tell the GPT or the chat, I want to produce a report that does blah, 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 and then it translates what I said into queries, into analysis pipelines that can help me generate those reports. In terms of model libraries, there exist a ton of libraries today, but they are siloed. They are in many, many formats. OWL, MOF, UML, LexisD, SQL. They are in all kinds of format out there. And there is a lot of good stuff there that we want to use. We want to convert it into this common ontological format such that we can build on each other's work. So today we have done a bit of that in the OpenCSA project because we had to, we didn't want to start from scratch, so we started adopting some of the standard ontologies. We did not cover all since we're only have a particular context, but as a group, as a community, between us all, we can decide which are the common libraries that are important to represent ontologically such that we can build on top of them. So we need to agree as a group, what are the important libraries that we need to convert ontologically such that we can use them, and we need to make this list easily findable. We need a registry of this list that I just think, okay, let's, for example, agree that if we said, let's say I want to use SysML-v2, then I can just declare I want to use SysML-v2. Automatically, this will be downloaded and environment provisioned to work on a model with that. Think of how software engineers, for example, they have different programming languages, Python, Java. Everyone is its own small ecosystem. So you can do that same effect. You say, I want to use in this, and then you get an environment provisioned with the right dependencies ready to be used. And then the area of examples, we all need examples because we don't want to work from scratch. Sometimes ideas are hard to communicate. An example is effective. Yuta mentioned today an example of an open source rover. So JPL has open sourced one of the rover designs, and they put all the hardware specification, but there is no system model for that. We need maybe to agree on a project like this, reverse engineer a system model, make connections to these subsystem specifications that are out there in the open source, and let's build and let's put all our ideas in a context that we can all agree with. Of course, this can be from multiple domains, but it needs to be sophisticated enough. So we should have like a range from simple examples to more sophisticated examples so that we can see how the ideas scale up. Okay, so in summary, I want to say that the point of the slide of this deck is to say we need to start working as a community to build an ecosystem that we can all contribute to, build on each other's work. If every group worked alone, we will not be there. We cannot evolve and move faster. And let's face it, we all live in challenging economic environment. There is no infinite supply of money here. So the little money we could each convince our sponsors to give needs to contribute to building a collaborative ecosystem. Some work has already happened in various groups. Let's keep the conversation going, agree on how we should collaborate, how can we work together so that we can move faster.